Single phase half wave converter drive. A single phase half wave converter feeds a DC motor as shown in this figure. The armature current is normally discontinuous unless a very large inductor is connected in the armature circuit. A freewheeling diode is always required for the DC motor loads, and it is one quadrant drive which is going to operate in the first quadrant. The application of this drive limited to a 0.5 kilowatts power level, and the waveforms for highly inductive load, the current IA is continuous armature current. When the thyristor of the half wave circuit is turned on at an angle alpha A, then the IS is going to flow through the motor IA, and when the thyristor is disconnected, the current is freewheeled through the freewheeling diode as the inductor is more. This is the current through the freewheeling diode, and this is the current from the source. The converter in the field circuit can be a semiconverter. A half-wave converter in the field circuit would increase the magnetic losses of the motor due to the high ripple content on the field excitation current. With a single-phase half-wave converter in the armature circuit gives the average armature voltage VA equals to Vm by 2 pi 1 plus cos alpha A, for alpha A is in between 0 and pi, where Vm is the peak voltage of the supply. With the semiconverter in the field circuit gives the average field voltage Vf equals to Vm by pi 1 plus cos alpha F, for alpha F is less than or equals to pi. That is equation number 2. Single phase semiconverter drives. A single phase semiconverter feeds the armature circuit as shown here. It is one quadrant drive again and is limited to the applications up to 15 kilowatts. The converter in the field circuit can be a semiconverter. The current waveforms for highly inductive loads as shown here, when the semiconverter is turned on at alpha A, then this is the output, and when these two are turned on, then this will be the output with minus IA, and this is with plus IA. Meanwhile, when the converter is off, then the freewheeling diode is going to give us support us with the current IA since it is having highly inductive load. Then the average current IA through the machine armature is motor armature will be a continuous current IA. With a single phase semiconverter in the armature circuit gives the average armature voltage VA equals to Vm by pi 1 plus cos alpha A, for cos alpha A is in between 0 and pi. Let this be equation number 3. Now with the semiconverter in the field circuit, the average field voltage Vf is given by Vm by pi 1 plus cos alpha F, for alpha F is in between 0 and pi. Let this be equation number 4. Single phase full converter drive. The armature voltage is varied by a single phase full wave converter as shown here in this diagram. It is a two-quadrant drive and is limited to applications up to 15 kilowatts. The armature converter gives a positive VA as well as a negative VA and allows the operation in first and fourth quadrants. During regeneration, for reversing the direction of power flow, the back EMF of the motor can be reversed by reversing the field excitation. The converter in the field circuit could be a semi or full or even dual converter. The reversal of armature or field will allow the operation in the second and third quadrants. The current waveforms for highly inductive loads, these two thyristors are turned on at alpha A, the current will be at IA, and when these two thyristors are turned on at pi plus alpha A, current will be the negative IA. Then the average current which is flowing through the motor is always a constant IA. A single phase full wave converter in armature circuit gives the average armature voltage VA equals to 2 Vm by pi cos alpha A, for alpha A is in between 0 and pi. Let this be equation number 5. With a single phase full wave converter in the field circuit gives the field voltage Vf equals to 2 Vm by pi cos alpha f, for alpha f is in between 0 and pi. This is equation number 6. Single phase dual converter drive. Two single phase full wave converters are connected as shown, the converter 1 and converter 2 here in the armature. Either converter 1 operates to supply a positive armature voltage Va, and or converter 2 operates to supply a negative armature voltage minus Va. Converter 1 provides operation in the first and fourth quadrant, and converter 2 in second and third quadrant. It is an 4-quadrant drive to permit 4 modes of operation. This is forward powering, this is reverse braking or regenerative braking, this is a reverse powering, and this is reverse braking or regeneration. And it is limited to applications up to 15 kilowatts again. The field converter could be a full wave or semi or dual converter. If the converter 1 operates with a delay angle of alpha A1, then the armature voltage VA1 is given by 2 Vm by pi cos alpha A1 for alpha A1 is less than or equal to 0 and pi, or in between 0 and pi. Let this be equation number 7. Then if the converter 2 operates with a delay angle of alpha A2, then VA2 is given by 2 Vm by pi cos alpha A2 for 0 and less than or equal to alpha A2 less than or equal to pi. Let this be equation number 8, where alpha A2 equals to pi minus alpha A1. We know that alpha 1 plus alpha 2 equals to 180 degrees in a dual converter. With a full converter in the field gives the field voltage Vf equals to 2 Vm by pi cos alpha f for 0 less than or equal to alpha f less than or equal to pi. Let this be equation number 9. This is regarding the different subtypes of the single phase drives. If this video is useful, please like, share and subscribe.